This is a walkthrough of our mechanical properties of materials virtual simulation. Now we're going to encounter mild steel for this virtual simulation. This is in courtesy of MHRD Government India Initiative, and thank you for providing this link. Now, once you click the link posted on our LMS canvas, you're going to be led on this dashboard. Okay. This dashboard has theory, procedure, self-evaluation, simulator, assignment, quiz, video reference, panels, and we're going to only click simulator later. Okay. But first, okay, let's discuss the theory of this experiment. Intention test and a test piece are fixed into grips connected to a straining device and to a load measuring device. The test involves straining a piece by tensile force generated to fracture for the purpose of determining one or more of the mechanical properties. Okay. Now, if we're going to consider the stress and strain graph of the mild steel, okay, as you can see here, this high slope or high linear slope of the part of the graph, you're going to encounter the following points, the lower end points as proportionality limit, the peak points at this region. Okay, this region is also known as the elastic deformation region. Okay, and the whole remaining areas yielding strain hardening necking is plastic behavior. For the earlier parts, which is the elastic deformation, this peak point here is the elastic limit. And once it slows down and goes to the point of yielding, this part is the yield stress. Now, if we're going to define the following variables, our x and y axis for this experiment, for the y axis, we have the stress and strain for the x-axis. The ultimate stress is denoted by sigma u. The fracture stress is sigma f. The yield stress is sigma y. And the proportionality limit is sigma BL. Now, however, the material behaves differently in each individual phase of plastic deformation. Area B here, this one, defines the flow region here. The material is stressed beyond its elastic loadability within the flow region. The stress changes very irregularly with increasing strain so that the wavy line results in the graph. In section C, strain hardening, the stress increases sharply and the plastic deformation also increases. At the maximum loadability, okay, the ultimate stress, the material cross-section begins to reduce in size and ultimately failure occurs. Okay. Increase sharply and the plastic deformation also increases. At the maximum loadability, the material cross-section begins to reduce in size and ultimately failure occurs or the fracture occurs. Now, we have the elastic deformation. The first phase of the stress strain damage is elastic deformation. Okay. When the stress acting on the material is removed, the material regains its original length. This is called the complete recovery or resilience. Again, the area of the elastic deformation is divided into two phases. The first one is material stretches proportionality or proportionally to the stress acting on it. This extension is also called linear elastic or proportional deformation. The point at which the linear elastic elongation is maximum is called proportional limit. Beyond this limits, elastic deformation still takes place. However, greater elongation occurs in this section. under increasing applied force. Therefore, the elongation or strain is greater than the increasing stress. Now we have the flow region B. Okay, this is where the highest flow point is accompanied by an initial sudden loss of quality. And we have the material hardening. If the stress is increased further, an increasing number of upright dislocation form in the crystal lattice prevents the movement of the previous still sliding dislocations. And for necking letter D, this is the maximum force, or if the maximum force is exceeded, the material begins to neck in, or the parts at the middle section of the material begins to form narrower. In the crystal lattice of the metal bar, so many dislocations have occurred that eh, the dislocation is already obvious. It forms voids and cavities. Apart from necking, the voids also cause the material cross-section to reduce. As said earlier, it will become a lot thinner. The stress now acts on an increasingly smaller cross-section, which enhances this process still further. Okay, now we have the percentage elongation. This is the increase in the gauge length of the test piece at maximum force, expressed as the percentage of original gauge length Li. The value of the percentage elongation depends on the gauge length chosen according to the BIS specifications. A gauge length of 5.65 the square root of area with 5 rods is to be used. Now we have the percentage elongation as the final length minus initial length all over initial length multiplied with 100%. Now the percent reduction is calculated as the cross-sectional area initially minus the amount of cross-sectional area at necking. Now, this is the final cross-sectional area all over the cross-sectional area initially prior subjecting the mild steel under tensile test times 100. Now, the tensile strength, this is the stress corresponding to the maximum force. This is calculated as tensile strength is equal to the ultimate load all over AI is equal to the amount in megapascal. Now, take notes of the units later. Now we have yield strength, which is calculated as equal to the yield load all over the initial area or cross-sectional area of the bar, mild steel bar. This is in terms of megapascal. Now take notes of the units later. Now, if I'm going to define yield strength, this is the metallic material exhibits a yield phenomenon. A point is reached during the test at which plastic deformation occurs without any increase in the force. Okay, now this is where the maximum strength of the materials has already reached. Now we have the modulus of the elasticity. It is the slope of initial linear portion of stress strain curve. This is calculated as slope times gauge length all over the initial cross-sectional area times, or this is in terms of gigapascal. Okay. Now, this is already the necking part, okay, as depicted or discussed earlier. Okay, as you can see here, we have the neck when the mild steel bar is subjected to the tensile test and, and the material is stretched. Okay. Now, this area is called the gauge length. Okay. Now, you may read this at your own pace once you clicked the link. Now, let's take the procedure. Please be guided with the objective. This is the study of mechanical properties of mild steel specimen under the tension load. Okay. Now, please be guided with the following. I'm just going to scroll it. It's up to you to explore it later. Okay. Now, if we're going to click this or this one later, at our simulator. Okay. This is just the illustration of the steps. Now, this is self-paced. You may explore this. And you're going to calculate the following parameters at the end of the experiment. The yield stress in Newton per meter or millimeter squared. This is in megapascal. Tensile strength in megapascal or Newton per millimeter squared. And the modulus of elasticity, gigapascal. The amount of elongation in percentage and the percentage of reduction in area. For the following formulas, okay, you may explore the theory parts, but now I'm going to click the simulator because once you clicked this link from our LMS Canvas, you're going to click simulator. This is where the actual simulation occurs. Okay. Now, the objective of the experiments, again, is to study the mechanical properties of the mild steel specimen. Okay? We have this apparatus as the universal testing machine, dial indicators, extensometer, scale, and vernier calipers. Now let us click this. Okay? For the first step, measure the initial diameter of the tension test sample in two perpendicular directions. Okay, we're going to click that one, and we are already given with the diameter as 12.62 millimeters, right? And DIY as 12.62 millimeters. Now, if we're going to add both, this gives us the diameter of the mild steel at 12.62 millimeters. Click next, this arrow, and please be guided. Just click where the arrow points at. Okay. The length of the specimen between the grips. Now, this is the initial length, Li, at 194 millimeters. And then click this one. Now, the distance, okay, between 2.5D is 2.5 times 12.62. Okay, this is the diameter. This is equal to 31.55 millimeters. Now, click the arrow. Okay. Now, this procedure entails putting punch marks on the mild steel specimen. Okay. Now click next. Okay. Now we're going to drag this specimen here and click the arrow. Now this is already the universal tension machine. Okay. And then let us click the arrow. Okay. Now we have the readings on dial A and B. This is called extensometer. Okay. Now we have the list count for this apparatus, extensometer, at 0.01 millimeters. Now let us click the button. Okay. Now we have the different readings for the loads of extensometers. Okay, so you can see here, there is already the formation of necking and fracture of the mild steel. Now let us click this one, and you're going to download the data later and then click the arrow next. Okay, now we have the graph slope, and then join two pieces of the test sample and measure the diameter at the neck of the specimen. Okay, now this is already the neck, and we're going to use the vernier caliper to measure the thinnest parts of the neck. All right, to measure final diameter of the specimen is 7.5 millimeters, apart from the initial diameter earlier, 12.56 millimeters. Now let us click this next. And we're going to measure the final length. Okay, the final length between the punch mark is equal to 86 millimeters. All right. And later we're going to calculate the following: yield stress, tensile strength, modulus of elasticity, percentage of elongation, percentage of reduction in area. Okay. We may check actually if our values are wrong. Say, for example, I'm going to input the wrong values since I don't have my calculators here. Say, for example, 156. Okay. Okay. Let us check. Okay. Now it's up to us. Now later you're going to input your values here. Okay. Mm. And now we have the following values. Okay. Now take notes of the following at your calculations. And you may ask help with other students or your classmates, because since this is a virtual simulation and online distance learning, apart from it, asking help from your classmates is also part of learning. Now, please be guided with the following links and instructions on our LMS. That concludes our virtual walkthrough for this simulation.